Lesson 16, Congruence, Transformations, and Classifying Triangles. Our objectives of this lesson are to draw, identify, and describe transformations in the coordinate plane, use the properties of rigid motions to determine whether figures are congruent and to prove figures congruent, classify triangles by their angle measures and side lengths, and also to use triangle classification to find angle measures and side lengths. The vocabulary words for this lesson are dilation, isometry, rigid transformation, acute triangle, equiangular triangle, right triangle, obtuse triangle, equilateral triangle, isosceles triangle, and scalene triangle. Let's start with the definition of dilation. A dilation with a scale factor k greater than 0 and center at 0, 0 maps xy to kx, ky. So we start with the little segment here, 0, 0, and then xy, whatever x and y are. And then we multiply the x and the y by k, so we get a new point. And you can see that it makes our segment longer. Dilations are like resizing pictures if you use Microsoft Windows Office. And you put a picture in and you pull the little tabs on the side and make your picture larger or smaller. Maybe we'll multiply by a whole number, or maybe we'll multiply by a fraction and make it smaller. So this is a resizing of a figure or shape. Let's look at an example. We want to apply the transformation M to the polygon with the given vertices. Identify and describe the transformation. So the first part, A, gives us M, which is a mapping of xy onto x minus 4, y plus 1. And then we're given some points, P, Q, and R. And we have P at 1, 3, Q at 1, 1, and R at 4, 1. If we look at that on a graph and go ahead and show the mapping as well, we start with PQR, and our new figure, our image, is P prime, Q prime, R prime. And what we've done is we've taken every point, like P is 1, 3, and we've moved it to the left by 4, subtracting 4 from the x, and we get negative 3, and we add 1 to y, so we have 4. So we have negative 3, 4, Q then is negative 3, 2, and R is located, R prime, at 0, 2. This is a translation, 4 units left and 1 unit up. Let's look at part B. This time we are mapping xy onto x negative y. So all of the x coordinates will stay the same, but our y's will become negative. So we start with ABC, and that would be our blue triangle. And this time we make all of the y's negative, and we get the red figure that you see there, A prime, B prime, C prime. This would be a mirror image. It is a reflection across the x-axis. Part C, we are asked to map xy onto y negative x. And we start with R is negative 3, 0, E is negative 3, 3, C is negative 1, 3, and T is negative 1, 0. Let's look at the picture. So we can see that we have R, E, C, and T for rectangle. And we map to Y. So if we look here, our X becomes our Y, it's at 0, and our Y becomes negative of X. So the R prime maps up here to 0, 3. And we do that with each of them. and we end up with a change in our rectangle, and this is a 90-degree clockwise rotation with a center of 0, 0, because it's about the origin. Part D, let's map xy onto 3x, 3y. So if we look at this picture, we start with this small triangle, this blue triangle right here, and we multiply everything times 3. And you can see that this becomes quite large and moved. This is a dilation with a scale factor 3 and center 0, 0. Representing transformations in the coordinate plane. We write the transformations just as we did before when we looked at these in Chapter 1. The translation is when we add or subtract a number from x and or y. In this case, our translation maps xy onto x plus a and y plus b. And the translation, a units horizontally, b units vertically. Remember that the x-axis is horizontal, so all of your movement is either left or right. And your y-axis is vertical, so all of your movement that has to do with y will be up or down. A reflection is when we make one of them negative. If we make x negative, it is a reflection across the y-axis. If we make y negative, it is a reflection across the x-axis. It's a rotation when we swap our x's and y's and make one of them negative. If we make the x negative and swap it for y, then we have a clockwise rotation 90 degrees. But if we make the y negative, then it's a 90-degree counterclockwise rotation. If they're both negative, it makes a 180-degree rotation. So it's like making it in a straight line, almost as though we have made a reflection, but you can see that the points themselves move. A dilation is when we map xy onto kx, ky, and k must be greater than 0. We can't use 0 for dilation. Some more definitions. An isometry is a transformation that preserves length, angle, measure, and area. Because of these properties, an isometry produces an image that is congruent to the pre-image. Remember, the pre-image is the original one. The image is your A prime, B prime, C prime. It is the new image. A rigid transformation is another name for an isometry. So a transformation that keeps all the angles and lengths the same would be any kind of transformation except for a dilation. In a transformation, the original figure is the pre-image, the resulting figure is the image. Translations, reflections, and rotations produce images that are congruent to their pre-images. These are isometries, or rigid transformations. Dilations with a scale factor where k is not equal to 1 produce images not congruent. They're either larger or smaller. For example, determine whether the polygons with the given vertices are congruent. And then we're given some vertices. So our first thing to do would be to plot them on the coordinate plane. Now let's take a look. They look the same, don't they? If I count lengths, each side is the same length as the other. They seem to have the same angles, but let's see if we can figure out what kind of actual transformation this is. If I start with A, I'm at -3, and I go over one more. If I subtract 1 from my x, I get -4. And then if I subtract 1, 2, 3 from y, I get the 2. -2. That should be. Let's try with b. If I subtract 1 from x and 4, 1, 2, 3, no, 3, I'm sorry, 1, 2, 3, I get 1, 0. Let's try the last one. I subtract 1 from x and 3 from y. 1, 2, 3. Yes, all of these have the same distance from the original point, and they are congruent. Triangle ABC can be mapped to PQR by a translation. XY, the mapping would be x minus 1 and y minus 3, as we stated before. Let's try another one. We have two figures, two triangles, and we should map them on the coordinate plane. Oh, I can look at this and see immediately that our numbers have grown. Because the blue triangle is our original image, this would be our image and pre-image, and this would be a dilation. They are not congruent. ABC can be mapped to PQR by a dilation with a scale factor k not equal to 1. XY, in fact, is mapped 1.5 times the original. Let's prove that the polygons with the given vertices are congruent. So we put them on the coordinate plane first, and we want to see, are they congruent? Do they look congruent? Well, ABC can be mapped to A prime, B prime, C prime by a translation. X minus 3 and Y plus 1, and then ABC, A prime, B prime, C prime can be mapped to PQR by a rotation of -yx. So we have taken this and moved it over 3 and up 1, and then we've taken it and rotated it around. Translations, reflections, and rotations can be called congruence transformations. Think back to chapter 1 and think back before that, where we're looking at transformations and we're looking at triangles. A triangle is a polygon with 3 sides. Triangles can be classified in 2 ways, by their angle measures or by their side lengths. So we have triangle ABC. AB and BC and AC are the sides of the triangle. A, B, and C are the triangle's vertices. An acute triangle has 3 acute angles. Equiangular triangles have 3 congruent acute angles. A right triangle has 1 right angle. An obtuse triangle has 1 obtuse angle. And we want to classify these. Let's look at BDC and classify it by its angle measures. So we are looking at BDC. So forget about the little part with A in it. This part doesn't count. So we know that angle B is 100 degrees. Angle C is 10. B is an obtuse angle. It's more than 90 degrees. So BDC is an obtuse triangle. Let's try another one. Let's look at ABD by its angle measures. A is 80 degrees, and our little part of D there is 20 degrees. ABD and CBD form a linear pair, so they're supplementary. That's ABD and CBD, these 2 angles here. Therefore, angle ABD plus angle CBD is 180 degrees by substitution. The measure of angle ABD plus 100 equals 180. So the measure of ABD is 80 degrees. ABD is an acute triangle by definition. All of its angles are less than 90 degrees. By side lengths, we have an equilateral triangle. It has 3 congruent sides. Isosceles triangles have at least 2 congruent sides. A scalene triangle has no sides congruent. Remember, when you look at a figure, you cannot assume segments are congruent based on appearance. They must be marked with scoring lines. Let's classify triangle EHF by its side lengths. From the figure, EF is congruent to HF, so HF is 10. This means it has 2 congruent sides, and it is an isosceles triangle. Let's look at triangle EHG. So EHG, the whole triangle. And we see that if we add these two together, this is 14, 11, and 12. By the segment addition postulate, we have EG equals 14. Since no sides are congruent, it is a scalene triangle. Let's use the triangle classification. Find the lengths of triangle JKL, the side lengths. So step 1, let's find the value of x. If we are told that JK and KL are equal, then that means that 4x minus 10.7 is equal to 2x plus 6.3. This is given. So JK equals KL, definition of congruent segments. 4x minus 10.7 equals 2x plus 6.3. This is just substituting in the values for JK and KL. We can add 10.7 and subtract 2x from both sides, and we end up with 2x equals 17.0. So x is 8.5. And we want to find the side lengths. So to continue the problem, step 2, we will substitute 8.5 into the expressions and find the different side lengths. So 4x minus 7, we get 23.3 for JK. KL is 2x plus 6.3. This also gives us 23.3, which it should, since we know that JK and KL are the same. JL is 5x plus 2, and we substitute in 8.5, and we get 44.5. Let's look at an application. A steel mill produces roof supports by welding pieces of steel beams into equilateral triangles. Each side of the triangle is 18 feet long. How many triangles can be formed from the 420 feet of steel beam? Okay, so the amount of steel needed to make one triangle is equal to the perimeter of the equilateral triangle. Remember, it says that each side is 18 feet long. So the perimeter is 3 times 18, which is 54 feet. Okay, we have 420 feet total. To find the number of triangles that can be made from 420 feet of steel beam, we simply divide 420 by the amount of steel needed for one triangle, which was 54 feet. So 420 divided by 54 gives us 7 7/9 triangles. Do we want to make a partial triangle? No. There's not enough steel to complete an 8th triangle, so the steel mill can make 7 triangles from a 420-foot piece of steel beam. We would round our answer down to the nearest whole number. For next class, bring your lesson notes to class, be ready to work similar problems in class, and be sure you learn the vocabulary words. They will be very important to you as we move along.